Hello, in this video I'm going to solve the following problem for you in abstract algebra on the topic of group theory. It is called Isbell's problem, after John Isbell, American mathematician. Okay, let m and n be relatively prime integers greater than 1. Suppose that in a group G, every 2mth powers commute, and also every 2nth powers commute. Prove that G is abelian. Of course, that would be a good idea if you pause the video at this point and try to solve the problem yourself first. Okay, now let us solve the problem. In order to solve the problem, let me remind you of a very famous theorem in elementary number theory called Bezout's theorem. So Bezout's theorem asserts that actually that if a and b are integers and both non-zero, and if the greatest common divisor of those numbers is the natural number d, then the existence of two integers r and s, or so that ra plus sb is equal to d is guaranteed. In other words, if you have GCD of two integers equal to d, that d can be written as a linear combination of the original numbers where coefficients are both coming from the set of integers. It is good to know that this is an existential theorem. So it doesn't tell you anything about how to derive numbers r and s, but it grants you that such numbers r and s indeed exist. So we do not have any control over them, we know that they exist. In this problem, if you remember when I was reading it, we are dealing with two natural numbers in m and n, so that they are relatively prime. So for me, in this problem, I am interested in a particular case of Bezout's theorem in which d is 1. So let me rewrite it again. If I have two integers, both non-zero, and if these integers are relatively prime, meaning that GCD of those numbers is equal to 1, then of course I am sure that integers r and s exist such that RA plus SB is equal to 1. So this is the special case of the more general case Bezout's theorem. But in this problem, because m and n are not only relatively prime, but also natural numbers greater than 1, I want to modify this second line so that it suits to our purpose for the problem that we have in hand. Okay, so I would say that let us assume that a and b are natural numbers and both be greater than 1, and of course relatively prime again, meaning GCD is still 1, I am claiming that I can grant the existence of two natural numbers x and y such that ax minus by is equal to 1. You will see why this will be crucial to have natural numbers in this problem in the way that I want to present the solution for it. Okay. So still, somehow I am saying that GCD, which is 1 in this case, can also be written as a linear combination of the same numbers a and b, but I have provided the linear combination in this form ax minus by, in which these coefficients are natural numbers, and instead of having a plus sign, I have a minus sign. Okay, how can I prove this? Very simple. I want to use this second line, which is a special case of Bezout's theorem, to grant this claim. How can I do that? I would say that when you tell me GCD of a and b are equal to 1, and when you tell me a and b are natural numbers greater than 1, so this assumption already grants the case, these two assumptions already grant me this case, because if numbers are natural number, they are automatically integers. If they are greater than 1, they are automatically non-zero, and you are telling me that GCD of a and b is 1. So all those conditions are fulfilled. So this means that this particular case of Bezout's theorem grants me the existence of these two integers such that Ra plus Sb equals to 1. This is exactly this line. Based on this assumption, I can write that. But I don't have that much control over R and S, I just know they exist. But can I explore something more about these numbers? For example, can any one of these integers be 0? Potentially yes, because they are integers, they might be 0, but not in this case. For example, if S is equal to 0, then what happens? Ra becomes equal to 1, but is that possible? Of course not. Why? Because R is an integer and A is a natural number greater than 1. It is not possible for this product to be equal to 1. So, it is clear that none of them can be 0. But what happens according to the positiveness, negativeness of these things, or these natural numbers? Because when you say they exist integers, they might be also natural. We don't know. So let us investigate this. For example, because I have two numbers, I have 4 possibilities. I want to explore these 4 possibilities. Both of them are positive. Both of them are negative. And one of them positive, the other one negative, which includes 2 subcases, yes? Just up to here, I just know these numbers exist. But I'm trying to see what more I can say about these numbers. Are they both positive? No. Because if both of them are positive, R and S are positive integers, A and B are natural numbers greater than 1, the left-hand side is definitely greater than 1, so this equality cannot hold. So if I know this, I already know that this hasn't happened yet, But this can happen? No. Because if R and S are both negative, because A and B are both positive, the left-hand side becomes negative, the right-hand side is positive, so it means that no, this cannot happen. But potentially, these 2 cases can happen, okay? And in both cases, I want to grant the existence of my natural numbers with that property. This one is extremely simple, okay? If R is positive, and because R is an integer and positive, so it is a natural number, let me define my X to be R itself. And S is an integer and negative. So it means that minus S is an integer and positive. So it means it is a natural number. Let me define Y in this way. Okay? But if this is the case, it is granted that X and Y are both natural numbers on the one hand, and on the other hand, let me now calculate AX minus BY. So it becomes A, instead of X I put R, minus B, instead of Y I put minus S. And then this RA minus plus SB. And if I ask you what this is RA plus SB, which is 1. So we are done. So it means that this is happening. We know this is happening. And we know that either this case should be true or that case should be true. If this case is true, the existence of such natural numbers with that property is granted. But this one is a little bit harder to convince ourselves about. Okay, so let us see that what happens. So let me write what I have. I have R and S are integers. I know RA plus SB is equal to 1. I know that R is negative, and S is positive. Okay. So for example, let me draw the real line, and this would be the origin. When I say R is negative and integer, it is somewhere on the left-hand side. Let us say R is here. Okay, but this is simple to understand because A is a natural number. Even though R is negative, I can add a suitable multiple of A, a suitable natural multiple of A, so that when I add it to R, it goes beyond 0. That is actually the Archimedean property of real numbers that we can also use for this special case. So when I say that R is negative, the existence of a natural number, let us say n sub 1, so that R plus n1 times B is positive. Sorry, when I was talking, I said a multiple of A. I want to have multiple of B. It doesn't matter because B is also a natural number greater than 1. So it is possible. So if I start with a negative number, by adding a suitable natural number multiple of B, I can finally go beyond 0. That is completely clear. And now, if you say that S is positive, I understand that minus S is negative. And I can repeat the same thing argument. I have an integer, a negative integer, so this grants me the existence of probably another natural number, so that what happens? Minus S plus n2a is greater than 0. Well, that's also the same line of argument, but repeating it for minus S. Okay, but now I define a new natural number to be the maximum of these two natural numbers, n1 and n2. So in other words, n is greater than or equal to n1 and n2 simultaneously. So what happens then? I will define my x in this way. I define x to be r plus n, the n that I just defined, multiplied by b, and I define my y to be minus s plus n times a. N is again this one. Let us see what happens. Can I make sure that this is a natural number? Because if it is not natural number, I am not allowed to call it. I want to grant the existence of natural numbers. So I have to make sure that this thing that I have introduced is a natural number. Of course, this one is a natural number because this combination is an integer and positive. So it's a natural number. But because n is greater than or equal to n1, so it is clear that r plus nb is greater than or equal to r plus n1b. If this one is already a natural number, and if this one is an integer greater than that natural number, of course this is a natural number itself. And for the same reason, this is true as well. Okay? Now, let me calculate ax minus by again by these numbers, numbers that I introduced. So it becomes a times r plus nb. Instead of x, I put r plus nb minus b times y, but y is minus s plus na, and I continue. So I open it up, it becomes ar plus anb minus b times minus s plus bs minus b times that is minus bna. And then this a and b minus b and a are gone. This is just ra plus sb. So it becomes ra plus sb, but ra plus sb is again 1. So again, I am done. So in any case that is possible, I was able to show that such natural numbers x and y with that property exist. Okay? Then you will see why this is important that I have to pick natural numbers. Okay. The reason that it becomes important is because now let us go to consider a group, any group, not the group that is given in the problem, any typical generic group, and let me say that, okay, n is a natural number, and let us say that a and b are typical elements of this group G. And then I am emphasizing that n is a natural number. Then my claim is that ab to the nth, of course you know that in normal algebra we can write a to the nth times b to the nth, but this is not possible here unless a and b commute. Okay, and that is not granted for any generic group unless we know about something about commutativity of these two elements. But no matter, even if they are not commutative, if they are not commutable, then you can write a, but ba to the power 1 unit less times b. And this n should be a natural number. Okay, so that is always true in any group. Okay, if I want to prove that, I can probably use a very simply mathematical induction, yes? If n is equal to 1, the base of induction, then the left-hand side becomes ab to the 1, which is just ab, but this one becomes 0, ba to power 0 is the identity element of the group, so it becomes ab again. So the left-hand side is ab, the right-hand side is b, the base of the induction is done. Now let us say that I have an I have a natural number k, and I assume that this is true for this k. I am assuming myself that this is true. Oh, sorry, this should be k. I am assuming that this to be true, and I want to show that this is true for the next step. So I want to show that ab to the power of k plus 1 is equal to a ba to the power of k plus 1 minus 1, which is k times b. So this is the question mark. I want to prove the validity of this equality based on the assumption that you see here. So I start from the left-hand side here, which becomes equal to ab to the power of k plus 1 can be decomposed as ab to power k multiplied by another extra ab. Yes, but now I can use induction hypothesis to replace ab to the power of k with this expression. So this becomes a ba to the power of k minus 1b. So this is what I put instead of this, but of course you see that I have to write a times b as well. But because I am working in a group, I know that every group is associative. I mean, the binary operation of every group is associative. So this means that instead of having the pair of brackets here, I can put the pair of brackets around these two. So this becomes a times ba to the power of k minus 1. This becomes ba, and then b will be left alone outside. But then you see what is happening? These are the same elements. One of them has power k minus 1, the other one has power 1. So I add the exponents, so it becomes a ba to the power of k minus 1 plus 1 times b, and that is exactly equal to the right-hand side. Okay, so I was able to show that in any group and any natural number and any pair of elements of the group, this relation holds. And this is the reason that I want to write Bezout's theorem in a form that I can have control over x and y to be natural numbers. Okay. Now I think that everything is in order. Now we can finally tackle the problem. So let us write the problem here. So what we know that G is a group. In this group, if you give me two mth powers, they will commute. And if you give me any pair of two nth powers, they also commute. I want to show that, okay, if m and n are relatively prime, that is extremely important. If that is the case, then I want to show that the group is abelian. It's a very beautiful problem from my perspective. I hope that you also enjoy that. So how can we prove this? Okay, so m and n in the problem are given to be natural numbers. They are given to be greater than 1, and the GCD of m and n is given to be 1. Yes, so what I will do, I will use that version that you see on the board, but instead of a and b, of course, I have m and n, but the conclusion is the same. So I can immediately conclude the existence of two natural numbers x and y, so that mx minus ny is equal to 1. So this we know. Okay, and now let us consider two group elements from here. So okay, so let me say that U is a group element, and then of course this means that U to the power of m is also a group element, because group is closed under the a binary operation of the group itself. And then this is called an nth power. And then let me give it a name. I write it capital U. Okay. So, and then I will do the same thing. So let me take V to be another group element. I raise this one to power n, and then of course it becomes a group element as well. So let me call this one capital V. Yes. Okay. Now I choose this U and this V, and I want to see what can I say about this combination. Okay, so you pick any arbitrary element from U and any arbitrary element, any arbitrary element U and V from G, and then you have M and N, raise one of them to power M, raise the other one to power N, and then you get two new elements from your group, put them here, and then put this exponent. Yes? I want to show that if the exponent you see is this mx, then within the pair of brackets I can commute them. So that is the whole point. Okay, so how can I do that? I want to use this theorem, which is valid in any group if the exponent involved is natural number. And it is here, because m was a natural number from the beginning. X, according to this version, is a natural number, so the product is a natural number. So I can safely use this theorem, and I can write it as u, and I can write it as vu to the power of 1 unit less multiplied by v. So what I did, I used this rule here. I gave the role of A to capital U, gave the role of B to capital V, and gave the role of N, which is a natural number, to this natural number mx, and just copy and pasted the right hand side. But I can decompose the middle term into the product of two powers. So I can write it as VU to the power of mx multiplied by VU to the power of minus 1 multiplied by V. Okay. But now, look, what can I do here? So let me change my color. So here, this is a famous theorem in group theory. This is the inverse of a product, so it becomes the product of inverses, but in the other order, in the reversed order. So I have to write this U inverse, V inverse. Okay, but of course you can see that this V inverse will cancel that V. This becomes the group identity element, so we can safely ignore it. But now look, U to the power of minus 1 is an mth power. Why? Because U is this one. So U to the power of minus 1 becomes U to the power of M to the power of minus 1. So it is the inverse of UM. But I can replace them. It becomes U inverse to the M. Okay, so this means that U inverse is an mth power. Okay, remember that. U inverse is an mth power. But UV to the mx is also an mth power. Why? Because VU to the mx can be viewed as VU to the x to the m. And this is definitely an element from my group, and then I have exponent m, so this is also an mth power. Okay, so U inverse is an mth power, VU to mx is an mth power. According to the assumption in the problem, every two mth powers can commute. So I will do it like this. I keep this V, I commute this U inverse with that, U inverse will come here, and then this becomes VU to the power of mx. But then of course this one and that one also cancel. This is the identity element, and what you get is VU to the mx. Okay, so what did I show? I showed that if U and V are mth power and nth power respectively, then UV to the mx is equal to VU to the mx. Okay? But remember, u and v are mth and nth powers. But similarly, I don't want to spend time on it. You can immediately conclude the same thing with nx exactly the same way. Okay, so I would say that uv then to the power of ny can also be seen that you can do it in the same way. Okay, so it means that if you have mx on the top, you can commute mth powers and nth powers. Okay, this is good. Now I want to push this one step forward, and I say that no matter if you have this exponent on top, every nth power can commute with every nth power. That is the next step that I want to do. Okay, so now what I will do, I will take one typical nth power, another typical nth power, and I want to convince you that they can commute even if this exponent is absent. Okay, so I can write uv as uv to the power of 1, but instead of 1, I write mx minus ny. And then what happens? I can break it into two parts. This one to power mx, and then this one to power minus ny. Now it becomes very clear what to do, yes? Instead of uv to the power of mx, I can write vu to the power of mx. And instead of uv to the power of minus ny, I can, if you want, I can do it in two steps. I can write it as uv to the power of ny, and then to the power of minus 1. Then it becomes vu to the power of mx. This one, I can replace them using this formula, so this becomes vu to the power of ny to the power of minus 1, which becomes this. Then, because the bases are the same, I can write the same base and combine the exponents. But that is nothing except 1 again, so it becomes vu. So I was able to show that if u is any mth power and v is any nth power, they can commute. Yes? Okay, the final step is to show that the group is actually abelian. So how can I show that the group is abelian? I would say that let G and haven't I used the letter H? So let us say G and H are group elements. We prove that what? We prove GH is equal to HG. This is the goal. If I can show that, it means we are done. Okay, but I start with GH, and the trick is to write G to the power of 1, H to the power 1, and instead of 1, of course you know the trick now, I put mx minus ny. So this becomes G to the power of mx minus ny multiplied by H to the power of mx minus ny. Okay, probably you can guess what we are supposed to do. We actually decompose this. We also decompose this. It doesn't matter in which order now you decompose, because you make sure that if I ask you what this is, you will tell me this is an nth power. This is an nth power, the same for these two. So we just showed that if you have any nth power and any nth power, you can commute them. So I will do that. I don't know if there is an optimal way to do it, but let us do it in this way. So I would write it like that. I will replace these two, nth power, we prove that they are commutable. So this becomes S, G to the power of minus ny, and then I have H to the power of minus ny. Now I am facing two nth powers, which was of course from the very beginning we know that we can commute them because of the assumption in the problem. So I can write H to the mx here, G to the mx here. This is nth power, this is nth power. From the beginning I know that I can commute them. Yes, but my goal is to have, again I will commute one more step. You see, this is an nth power, this is an nth power. I commute them one more step. And then this goes to the other side. Yes? And now look, they can be combined because the bases are the same, and these can be combined because the bases are the same. And now if I ask you mx minus ny, you will say it is 1, so it becomes h to power 1, g to power 1. So I started from gh, and I ended up with hg. So for any pair of typical elements of this group, I was able to show that gh is equal to hg, so this means that this group is indeed abelian. Okay, so if you want to summarize, we actually wanted to use this rule. To know this rule, to use this rule, I needed to have this exponent a natural number. This is why I modified Bezout's rule, Bezout's theorem, in a way that it matches with our purpose more. And then I started from any typical nth power and any typical nth power of the group, and I showed that if the exponent is mx or ny, these two can commute. And then the next step, I pushed this a little bit forward, and I said that every nth power can commute with every nth power, even if you don't see these exponents. Okay, and that was the proof. And then after that, I started tackling to the problem. Finally, I picked two elements from my group, no matter what they are. I started from GH, and I did this algebra. So here, in this, between these lines, I used the two assumptions given in the problem from the beginning, that mth powers commute, nth powers commute. But I also, for example, used here an nth power and an mth power can commute based on what we proved here. Okay. I myself actually was fascinated to see this gymnastics of powers, because in abstract algebra, as the name suggests, it is very abstract. I don't know if we can actually develop some kind of intuition by solving harder problems of this type, because this is very abstract. So there is no guiding line, there is no imagination. Might be if you're an algebraist, by working harder and harder probably, or seeing a lot of problems, you finally develop an intuition about these kinds of things. Of course, we become better by practice, but still it is very abstract, and I really enjoyed this, and I wanted to share it with you. So hopefully you enjoyed the video, and the video was useful for you. Until the next video, be safe and goodbye. Thank you.